We will begin by outlining the basic steps required to obtain the final magnitude graph. Step 1. Solve for the transfer function h of omega.
Step 2. Convert h omega to standard form.
Step 3. Find the magnitude of h of omega.
Step 4. Take the log base 10 of this magnitude and multiply it by 20.
Step 5. Identify all zeros and poles.
Step 6. Utilize the table to determine slopes of lines.
Step 7. Graph each individual component.
Step 8. Graph the summation of each individual component.
We will continue by discussing an overview of what a transfer function is.
The transfer function in the frequency domain analysis of a system involves the amplitude of the output as a function of the frequency of the input signal.
H of omega is y of omega divided by x of omega, or in other terms, the output voltage divided by the input voltage of your system.
Isolating for h omega is your first step in solving for a Bode plot.
We will not be going into detail of how to solve for h of omega, but in turn following an example of where h of omega is already given. The next step is to convert the transfer function into the standard form. In order to do so, it is necessary to factor out all constants to get each pole and zero into the form 1 plus j omega over z. This will simplify the analysis of each pole and zero when graphing the magnitude plot, and allow you to be able to use the general tables for graphing.
This is an example of a transfer function h omega being converted into standard form. In the numerator, you can see that 10 was factored out of the 0, j omega plus 10, while in the denominator, 3 was factored out of the pole, j omega plus 3, and 50 was factored out of the pole, j omega plus 50. The resulting 0 and poles are now in the form 1 plus j omega over z. Z will be what determines the value of the omega when the magnitude is equal to 0, as we will demonstrate later. Once you have the function in its standard form, you can now take the magnitude of each 0 and pole individually. When working in the units of decibels for magnitude, you take 20 times the log base 10 of each 0 and pole, as well as the constant. By logarithmic expansion, we can see that the zeros in the numerator will have positive magnitudes, while the poles in the denominator will have negative magnitudes. This chart shows the corresponding magnitudes for each type of term that may appear in a transfer function.
Here is a table detailing the 5 most common factors seen after converting h of omega to the standard form. A common factor, k, is depicted as a straight line at 20 log of k. A 0 at the origin is seen as a line with a slope of 20 decibels per decade that passes through 1. A simple 0 is graphed such that the line is 0 until it reaches its value z, and then rises with a slope of 20 decibels per decade. A pole at the origin is seen as a line with a slope of negative 20 decibels per decade that passes through 1. A simple pole is graphed such that the line is 0 until it reaches its value z, and then falls with a slope of negative 20 decibels per decade.
This is an example of graphing individual components of a Bode magnitude plot and the manner in which these components are combined. The steps outline that each pole and zero should be graphed individually with dotted lines. When every component is graphed, you must identify the omega values in which the graph is changing. At these points, different slopes will be added in order to finalize the completed graph. For example, in this problem, the transfer function had a pole at the origin, a simple 0 beginning at 2, and a simple pole beginning at 10. At point 2, the negative 20 dB per decade slope from the pole at the origin must be added to the simple 0 of slope 20 dB per decade. This in turn leads to a slope of 0, seeing as though negative 20 plus 20 is equal to 0. At point 10, the simple pole comes into play, and now you must add negative 20 plus 20 minus 20 together to give you an overall slope of negative 20. Since no other components are added thereafter, this is your final graph. This is the manner in which you approach the summation of components of each Bode plot.
This is an example problem that we will go through in its entirety. Here, h of omega is equal to 5 times j omega plus 2 divided by j omega times j omega plus 10. We need to factor out the 2 in the numerator as well as the 10 in the denominator. You can see that the constants will reduce down to 1. The resulting transfer function in its standard form has a simple 0 at 2 due to the 1 plus j omega over 2, a pole at the origin due to the j omega in the denominator, and a simple pole at 10 due to the 1 plus j omega over 10. The next step is to take 20 times the log base 10 of each component and then graph their individual slopes shown as dotted lines here. The simple 0 at 2 will have a positive slope of 20 decibels per decade, whereas the pole at the origin and the simple pole at 10 will both have a slope of negative 20 decibels per decade. The log of 1 is 0, and so we will have a constant of 0. Now we can find the resultant Bode plot by summing the individual components as shown by the solid purple line.